Hello everyone, I am Raghanya pursuing M.Sc.Ed Physics at RI Mysore. In this video, I'll be explaining briefly about long range order in a system of long rods, that is in special types of liquid crystals. I'll be covering a brief about liquid crystals, what are commonly known as long rods, order parameters which are used to explain orders in liquid crystals, and then we'll see the factors which are useful in characterizing liquid crystals, and we'll look at types of liquid crystals and long range order. Liquid crystals are a state of matter that lies between conventional liquids and solid crystals. Unlike isotropic liquids, liquid crystals exhibit anisotropic behavior and their properties depend on the direction in which they are viewed. Usually it is defined by a director. So you must be aware of these things. The liquid crystals also have widespread applications, including liquid crystal displays used in digital devices. This must be familiar to you. So this diagram shows the different organization of rod-shaped molecules with different molecular order. So the first one is a crystal, the second one is a liquid crystal, and an isotropic liquid. And the second part shows the organization of rod-shaped molecules in different liquid crystal phases. As the temperature increases, we move from left to right, and the director's direction is shown here. The first phase is nematic, and then we have cholestric, and then we have smectic A and smectic C. Some of the common applications of liquid crystals are display technologies, electro-optical devices, sensors and switches, and photonic devices. I will not be going into the details of these applications. Coming to long rods in liquid crystals, so they are usually the molecules or units in liquid crystals which have very long shape, as you can see in the figure. The alignment of these long rods within the liquid crystal system leads to intriguing phenomena. Most substances exhibiting liquid crystal properties consist of elongated rod-like molecules. These rod-shaped molecules are easily polarizable and can orient themselves in specific ways. This is an image derived from the source. It is about the common liquid crystalline phases observed in colloidal suspension of rod-like viruses. This is something peculiar and new to us. Even viruses in a colloidal suspension shows phases similar to liquid crystals. This is what is observed here. So coming to order parameter, in order to quantify the long range order in liquid crystals, we need to define order parameter, and the Mayer-Sop theory is an approach which is used to develop a theory of spontaneous long range orientational order in nematic phase of liquid crystals. I will give more detail about orientational order in the upcoming slides. It is based on molecular field method and is analogous to Weis theory of ferromagnetism, which you must be familiar with. Each molecule is thought to be in an average orienting field uncorrelated with its neighbors. The long-range orientational order parameter, denoted by S, is used to define the degree of alignment in the nematic phase. So this is a graph of orientational order parameter varying with temperature. Liquid crystals are materials with a unique molecular structure. The long molecular axis makes an angle theta with the director, as shown here. This is in particular we are talking about nematic phase here. Order parameter S is used to quantify the level of order in a material. It is defined as half times the average of 3 cos squared theta minus 1. In an isotropic liquid, the order parameter is 0. As you can see here, isotropic liquid has a random orientational order. Therefore, the average term will give us 0. Similarly, in ideal crystals, we have order parameter of 1 because ideal crystals, the rods are perfectly aligned and there is no randomness in the orientation. Whereas liquid crystals have order parameters between 0.3 to 0.9. Here you can see the order parameter has an intermediate value in nematic phase. The order parameter is also temperature dependent in the case of liquid crystals. This is again a graph showing the variation of order parameter S with temperature. Here you can clearly see the different phases of liquid crystals. First, the smectic C is converted to smectic A and then it transitions to nematic phase, and then we have the order parameter going to 0 at the point of transition to isotropic phase. So in isotropic phase, the order parameter is 0 and this is the temperature of transition temperature from nematic to isotropic. Anisotropy in liquid crystals, it is the result of molecules' propensity to point along the director. It means that the material's qualities are dependent upon the direction of measurement. So for example, cutting a piece of wood with the grain is easier than cutting it against it. So the special optical qualities that scientists and engineers use in a wide range of applications are caused by the anisotropic nature of liquid crystals. Here we will characterize some factors in relation to liquid crystals. These are orientational order, bond orientational order, and positional order. Orientational order measures the tendency of the molecules to align along the director. Bond orientational order defines the line connecting the nearest molecule centers, and positional order measures the translational symmetry. That is, the degree to which a typical molecule or a collection of molecules exhibits translational symmetry, just like a crystalline material does, is referred to as positional order. And as previously said, orientational order is a measurement of molecules' propensity to align along the director over an extended period of time. And we have also seen the order parameter related to orientational order. Coming to bond orientational order, it describes a line joining the centers of the nearest neighbor molecules without requiring a regular spacing along that line. So consequently, there is only a short range positional order along the line of centers, but reasonably a long range order with respect to that line. So what are polymorphism and mesophases? Polymorphism is the situation in which many phases are exhibited in the liquid crystalline form. It is a condition present in the majority of liquid crystal substances. The term mesophase is used to describe the subphases of a liquid crystal material. So, mesophases are formed by changing the amount of order in the sample. So, each phase has different order in different types of factor. That is, it may have difference in orientational order or positional order, so on. So the order is imposed either in one dimensions or two dimensions, or by allowing the molecules to have a degree of translational motion. Coming to the type of liquid crystals, we can see that each type of liquid crystal is associated with a type of long range order. In nematic phase, the rods align predominantly in the same direction, parallel or anti-parallel. This system has long range orientational order. Coming to the smectic phase, the rods form layers with each layer having a preferred orientation. The layers slide past each other, allowing flow. In columnar phase, the rods stack into columns, maintaining the alignment along the column axis. This system has long range positional order. So, to conclude about long range order in liquid crystals, the liquid crystalline long range order is important for various studies and applications. Liquid crystals display long range order while retaining molecular mobility, and different forms of long range order will result in macroscopic anisotropic features. Thank you.